The next type of primary source we're going to look at that's used in power stations is nuclear fuel. So this is basically looking at nuclear fission. So you'll need to go back to subtopic 7.2 and have a look through nuclear reactions if you need to brush up on nuclear fission. I won't do that here. We'll just sort of continue on assuming that you've got that understanding. So in this case, it's the energy from the fission of uranium-235 usually. There are other fuel sources, but we'll just refer to uranium-235. That is used in a nuclear power station, and the use of that is, as we've seen previously, is basically used to heat water, and then again that water that's heated produces steam. The steam goes on to turn the turbine. So in this case, though, the process is a little bit more involved than what it was for fossil fuels. So we'll just take a little bit of time here to identify what the key aspects are. It's not quite as straightforward as just allowing combustion of a substance the way that it is for fossil fuels. It's a little bit more required to ensure that there's the safety of people that are around these plants, and some of the other aspects that are important to consider in terms of the production of the energy itself. Now, the first thing to note here is that when we're looking at uranium-235, we find that in uranium ore, so ore that's dug up out of the ground, and uranium ore contains about 99% of uranium-238. Now, uranium-238 is actually a fairly good absorber of neutrons, so when you're talking about fission, it means that having a lot of uranium-238 is not all that desirable because it's not going to undergo fission, and so we need to make sure that we can do something with the uranium-235 instead. Now, given that there's only sort of less than 1% of uranium-235, we actually need to have more than that. So to be fissionable, there must be about 3% of uranium-235. And so that means we need to go through a process that's known as enriching the fuel. So the fuel must first be enriched. So you might hear the term enriched uranium. That basically means that the amount of uranium-235 has been increased, and so basically it's the purpose is to boost the ratio of uranium-235 to uranium-238. So that's the first thing that's important. So comparing that to fossil fuels, you don't really need to do too much to coal in order to use it in a nuclear power plant, but if you're using uranium, you've got to go through this process of enriching the uranium first to make sure that it can then be used in a power station. So you notice there that in having to enrich the uranium, there's a bit of an energy loss there as well. Now we'll jump to a diagram here. So this diagram just shows the parts of the power plant that uses nuclear fuel that's a bit different to what it is for a fossil fuel power station. And notice over the right hand side here the turbines and generator and those sorts of things have been omitted from this diagram. So this is basically sort of this section here is sort of replacing the furnace of a coal-fired power station. You'll notice that there are a few extra bits and pieces here that we need to be concerned with. The first thing we should talk about here are the uranium fuel rods. So that's where you'd find the enriched uranium. So that's where the fission is going to occur in the nuclear power station. You can see there that there are a few other parts to the nuclear power station that we need to consider. The ones that we'll consider here are the graphite moderators and control rods. We'll talk about some of the other aspects later on when we start to get to the safety aspects. So the first thing to note here, we'll talk about the graphite moderators. So the reason why we need those moderators is that when we have neutrons emitted from fission, they tend to be fast. They have a high amount of kinetic energy. So neutrons emitted from fission have high kinetic energies, And the problem with that is that means that they're moving too fast to be able to go on and cause any other fission reactions. So too much to cause further fissions. And so as a result, they need to be slowed. And that's basically the purpose of the moderator. And by slowing them down, they are now referred to as thermal neutrons. So basically, they're sort of not too much above what the surrounding material is. So they've slowed back down. Their kinetic energy is much slower, and they need to be slowed by a moderator. So the moderator is literally there to moderate the speeds of the neutrons. Moderators need to be pore absorbers of neutrons. So they don't actually absorb them and stop them entirely. They just slow them down. It's an important point to note. There are a few past exam paper questions that talk about some of the properties of moderators. So they must be pore observers of neutrons. And the reason for that is so they only slow, not stop, the neutrons. Now, in the example above, we've got graphite as the moderator. Some other substances, or another substance that's often used, is heavy water. So that's water molecules that contain H2 isotopes. So it's not just a proton, it's H2, so a proton and a neutron. So they're two of the common the moderators that you might see. Now the control rods have a similar but different purpose. So the control rods, as the name suggests, are about controlling the output, or to regulate the power output. So if we were to allow the fission reactions to just sort of start and continue, there's the chance that they would actually start to produce too much energy. So the power output might get too great, so we might need to sort of peg it back a little, or it might be dropping too small and we might need to increase it, and in some cases might even need to shut down the reactor. So in shutting down the reactor, maybe that could be in the case of an emergency where there's been a malfunction or something is not happening the way it should. The reactor can be shut down by using the control rods, and that's basically by just sort of raising or lowering the control rods. So in that diagram before, just lifting or lowering them to allow those neutrons that are sort of being released from the fuel rods to then go on and bombard other uranium-235 nuclei in other fuel rods. Now, for control rods, they need to be good absorbers of neutrons. And a substance like boron is a good example of that. So good absorbers of neutrons, and the reason for that is so that there are less neutrons to cause further fission reactions. So there's the two critical things in the reactor of a nuclear power station. The last thing we need to mention there as well, though, is the heat exchanger. So the heat exchanger was that structure on the right hand side, and it's basically taking the energy from the fission reactor itself, and so it transfers the internal energy from the reactor to the water that's vaporized that produces steam. And that steam again that is used to power the turbine. So in that situation, you'll notice that in the diagram before, we've basically got sort of two separate systems that are interacting through the heat exchanger. So the heat exchanger itself, the main purpose of it is to separate the potentially radioactive material in the reactor. So if you think about the fuel rods, the control rods, the moderators, there's a lot of radiation that would be in the reactor, and so we don't really want that getting into water that's then going to go and power a turbine where people are going to need to be working in and around the turbine. So we need to separate that radioactive material and the water or steam, or water and steam, used to turn the turbine. There are a number of different systems for these nuclear power plants. So one of the most common is the PWR, which is a pressurized water reactor. The reason why it uses pressurized water, it's just easier for it to flow through from the reactor through into the heat exchanger. But like I say, there are other methods that can be used in power stations that use nuclear fuel, but that's just the one that we've had a look at here. The main thing, though, is actually looking at what happens in the reactor itself in terms of the moderators, control rods, and the energy exchange that occurs there. In the next video, we'll have a look at some of the safety issues that are associated with nuclear power, and then after that, we'll go on to some of the other sources such as wind, solar, and pumped storage as well.